Now, the bending of light as it travels through different mediums of different index of refractions is not completely independent of the wavelength of that light. So you can get what's called dispersion. Dispersion is when different colors bend in different ways, different degrees, as they move through a medium. Blue light, as short wavelength light, versus red light, which is long wavelength light, behave slightly differently when they move through glass. So for example, the speed of blue light is actually a little bit smaller than the speed of red light. This leads to a different index of refraction in a material depending on the color of that material. So white light, the light that you have, at your home, incandescent bulbs over your head, fluorescence and so on, the sun, contains a myriad of colors all combined together. When you take the entire rainbow of color and put it together in light, we call that white light. When white light strikes, let's say, a glass prism, the light is bent. We talked about rays of light being bent. But the index of refraction for flint glass is around 1.5 or so. It varies very slightly on wavelength. So for example, blue light at 400 nanometers has a higher index of refraction than red light at around 700, 750 nanometers. Not much, right? It's in the third decimal place here. So you're talking about a change of a few percent, but enough that when white light shines through this prism, you can actually get out what's called a spectrum. We call that the rainbow, right? So blue light is bent more than red light in the material and then when the material emerges. So we change white light into its constituent colors. Now, for a long time, it wasn't known why that happened. When Isaac Newton played around with this 400 years ago, it was thought that maybe the prism adds color to light. Well, he actually did a really wonderful experiment when he took a prism into a rainbow, took one of the colors, let's say green, sent it through a second prism to see if that second prism added color, and it didn't. It just spread out the green light more. So white light contains all of these colors, all the colors in the rainbow, and we can spread those out using what's called a prism, or a grating does the same thing, which a grating is just a lot of fine lines in a plastic or glass etched piece of glass. Prism is probably the most familiar thing for creating rainbows. Water droplets do the same thing. If you look in your book gives diagrams about a water droplet. A water droplet does two of the things we've talked about so far. There's total internal reflection inside the water droplet. So the sunlight that's behind you hits the water droplet, bounces around in the water droplet, and comes back into your vision. And because as the white light from the sun moves through that water droplet, the different wavelengths of light get bent different amounts, which gives you the spectrum that we see, which gives you that rainbow effect. So for a rainbow, to see a rainbow, you have to have a light source behind you, typically the sun. There has to be water droplets on the other side of you, away from the sun, so that light can be reflected back at you. And rainbows are almost always circular. You'll see that partially circular feature of a rainbow. If you're actually floating in space or way up in the atmosphere, you can actually see a complete rainbow, a complete circle. Where the blue light, the violet light, is bent the most, center of the rainbow, and the red light is above. You can get secondary and tertiary rainbow effects for double and triple total internal reflection inside a water droplet. They're weaker rainbows, but they still exist. So this dispersion is just basically breaking up white light into a variety of colors because the different wavelengths travel at different speeds in the medium of the index of refraction. In a vacuum, all the wavelengths travel at the speed of light. There is no difference. But when you enter a medium that isn't a vacuum, which has some index of refraction, then the colors change slightly. So in camera optics, this becomes very problematic. It's called chromatic aberration. Aberration means error. Chromatic means color. So if you have a camera lens, you'll actually see it's not just a single lens. It's actually a very complex inner working of many lenses to undo this chromatic aberration. And we'll also see that mirrors don't suffer this. It's only when material travels through a medium of a high index of refraction, where the index of refraction depends on the wavelength of light.